all gases have essentially the same gas properties. They all have low density. Density is mass per unit volume. If we take the same size container and fill one with solid, one with liquid, and one with gas, we find that the solids are close packed, so you get lots of particles, lots of mass per volume. Liquids, their spacing is larger so that the particles can move around each other. Less mass per volume. By the time that you are a gas, the distance between the particles is so significant that they have very low density. Gases need to become volatile. They need to be able to enter the vapor phase from the liquid phase, which means having a low mass is an advantage to them. They have low interparticle attractions. If these two gas particles were attracted to each other, then they might be tempted to form back into a liquid. So we do see that a lot of gases are nonpolar. They're compressible, which means that we can squeeze them down, and we can squeeze them down because there is a large empty space between the gas particles. They occupy the entirety of their container. We know that solids have their own three-dimensional shape. This pen is a solid. It has its own three-dimensional shape. If I were to put it into a beaker, it would retain its shape. If I could melt this plastic down and turn it into a liquid, then the liquid would occupy the bottom part, because of gravity, of the container. But if I could vaporize this pen, then the vapor of the pen would occupy the entire container. And last, gases exert pressure. So we have to talk about pressure and where it comes from and what it is that we can do that will affect pressure. Pressure is a manifestation of gas particles colliding with the walls of the container. Pressure is a force that is distributed over a surface area. So if this red dot is a gas particle inside this container and it is in motion, every time it strikes the inside walls of the container, it generates a pressure. Those collisions generate pressure. So, what can we do to this system that will change the pressure of the gas inside the container? If pressure is because of collisions with the wall, then I could just go ahead and add another gas particle. If I change the number of gas particles, then I change the number of collisions. So the number of particles, n, measured in moles, is going to have a direct relationship to pressure. If I make the particles move faster, then the time between collisions would be smaller. I would have more collisions per second, and I can make them move faster by increasing the temperature. Heat energy is kinetic energy. It's the energy associated with motion. So if I increase temperature, I increase the speed at which the particles move, and not only do I get more collisions per second, I get more violent collisions per second, which is really going to help with the pressure. And then there's one other thing that I can do. If pressure is the number of collisions with the walls per second, what if I made the distance between the walls smaller? If I decreased the volume, then I would get more collisions in the same amount of time than if the volume were bigger. So the number of gas moles, the temperature, and the volume all play into the relationship of pressure. The kinetic molecular theory of gases tries to take all of these observations and make them make sense. We do make a couple of assumptions. We assume that the gas particles are independent, that if there are two gas particles inside a box, then the space between the particles is sufficient that they can navigate around each other without coming into contact. They will come into contact eventually, but it's not significant. Now, if these two gas particles were the same type of gas and they're acting independently, then it would make no difference at all if they were different particles. If one was a nitrogen and one was an oxygen. Okay, so the independence is true for whether it's a sample of pure gas or for if it's a mixture. That there are no attractions between the gas particles, that there's nothing wanting these particles to clump together. And that the particles are always in motion. They're in constant random motion in straight lines, and they will continue in straight lines until they meet a barrier, and then they will collide with it, and those collisions will be elastic. This is Newton's laws of physics, Newton's laws of motion, that a body in motion stays in motion unless acted upon by an external force. Okay. And then the speed is relative to temperature, because temperature is a gauge of what the heat is, and heat is kinetic energy, and the numerical relationship of kinetic energy is half mv squared, where m is mass and v is velocity or speed. So if I have particles and they're independent inside this container, then what I've got is a population. And inside a population, we're not going to have just one number. What we're going to have is a range. And so if you were to plot speed on this axis, against amount, we would find that the gas population has an average speed at a particular temperature. Now, when we change temperature, we increase temperature, if there is a particular part of this graph that we can highlight and say, that's really high speed, when the particles hit the wall at that speed, they're really having an effect on pressure. What happens when we increase temperature is we move the average speed to a higher number, but we drastically increase the number of particles that we count as being high speed. These are the ones that make real, meaningful, impactful collisions with the inside of the container. So temperature really does have an effect on pressure. Okay, so if we recap, here's a container. If I put more particles into the box, I get more collisions. More collisions means more pressure. So as the number of moles of gas go up, pressure goes up. If I increase temperature, then I increase the energy of the particles, which means that their average speed increases, but also the number of particles with high speed collisions increases. So as temperature goes up, pressure goes up. And if I reduce the size of the box, then I get more collisions per second because the walls are closer together. So if I reduce volume, pressure goes up. The relationships that the kinetic molecular theory of gases gives us has allowed us to develop a number of gas laws. Let's look at the first one. The first one's called Avogadro's law, and it says that the volume of a gas is proportional to the number of moles of that gas. That at the beginning, the initial number of moles, N1, will give me a volume, V1, and it will have the same relationship to a new number of moles and a new volume. In fact, this is so strict that we have discovered that 1 mole of any gas, remember all gases are acting independently, so all the particles inside this mole of gas are independent, so it doesn't matter what the identity of the gas is. 1 mole of any gas occupies 22.4 liters at conditions that we call STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of atmospheric pressure. Okay, let's put this to a question. How many moles of helium gas are in a balloon that has volume of 1 liter? And I'm going to have to do this question at 0 degrees Celsius and 1 atmosphere. Okay, working on the assumption that the balloon is inflatable, so the balloon's allowed to change volume when the number of moles changes volume. V over N equals V over N. 1 mole generates 22.4 liters of volume. So how many moles will generate 1 liter? This is how we're going to set this up. Now, I need to solve for this. This is the number that I need to find, and currently it's a denominator. I need to turn it into a numerator by moving it across the equal sign. It will turn from being a denominator into a numerator, and I'm going to move that number over, and they will switch places. So N2 is equal to 1 liter divided by 22.4 liters times 1 mole. And those liters cancel. And my answer comes out to be 0.0446 moles of helium occupy 1 liter of a balloon. And in fact, it isn't just for helium, it would be for any gas. The next gas law that we'll look at is Boyle's law. Boyle's law represents the relationship between pressure and volume. Now we know that pressure and volume have an inverse relationship. So the pressure times the volume under our first set of circumstances is going to be equal to the pressure times the volume at our second set of circumstances. Here's a question. A 4-liter balloon contains helium at 3 atmospheres of pressure. What is the new pressure if the balloon is compressed down to 2.5 liters? So I'm going to take 4 liters at 3 atmospheres and squeeze it down to a new pressure. So a little bit of logic tells us that we're expecting a number that should be larger than that. Let's see if that happens. Okay, P1 V1 equals P2 V2. If this is the pressure at the beginning and the volume at the beginning, then the question is asking, what is the pressure at the end? this is the number that I have to find. Okay, so P2 is going to remain where it is, and then V2, well, I'm going to have to move it out of the way. And as I move it across the equal sign, it moves from being a numerator to being a denominator. So I'm going to rearrange P1 V1 equals P2 V2 to P2 is equal to P1 V1 divided by V2. Okay, and once I have that, I can just put the numbers in. The pressure at the beginning is 3 atmospheres. The volume at the beginning is 4 liters. The volume at the end is 2.5 liters. Those liters cancel. It's going to give me an answer that comes out in atmospheres, and that number turns out to be 4.8 atmospheres. So I started with a larger volume, compressed it down to a smaller volume. I was expecting the pressure to increase, and it did. So I probably got that one right. Our next gas law is Charles's law. Charles's law shows us that the relationship between temperature and volume is direct. The volume of a gas at a particular temperature under those circumstances will be equal to a new volume at a new temperature. So let's throw some numbers at this and see if we can do a calculation. A balloon of gas at 18 degrees Celsius has a volume of 2.75 liters. What is the volume at 45 degrees Celsius? Well, if V1 over T1 equals V2 over T2, and the question is asking me to find the volume under the new conditions, so it's asking me for V2, means I have to take the T2 and put it across the equal sign. It will move from being a denominator up to being a numerator. So V2 is equal to V1 T2 divided by T1. And if I go ahead and I put those numbers in, 2.75 liters times 45 degrees Celsius divided by 18 degrees Celsius, those numbers will cancel, gives me an answer of 6.87 liters. And I might walk away from the calculation happy at this point. And then I remember that if temperature and volume really are directly proportional to one another, and the degrees Celsius scale allows numbers to be both positive and negative, that a negative value of temperature plugged into this equation would generate a negative volume. And volumes cannot be negative. They exist in three-dimensional space. They're always positive numbers. So something is wrong. You must use Kelvin. If you put Celsius into your equation, your answer is wrong. This must be performed in Kelvin. Okay, so that 45 becomes 45 plus 273. Remember, 0 degrees Celsius is 273 Kelvin, and a degree interval in the Celsius scale and the Kelvin scale is the same number. And down here, that would be 18 plus 273. So my new number at the top is 318 Kelvin, and my new number at the bottom is 291 Kelvin. Those Kelvins cancel. And now my answer is not 6.8 liters. It's 3. Mathematical calculations need to be performed using Kelvin. You cannot use degrees Celsius. If we put all of the gas laws that we've seen up to this point together, we get this equation. PV equals nRT. This is known as the ideal gas equation. Gases behave ideally when they are warm and not under very high pressure. If you pressurize a gas very highly, then it wants to start to liquefy. If you make the temperature of a gas very low, then it wants to liquefy. If you stay away from the boundaries and just let the gas be a gas, then the particles act independently. And this is a good approximation for gas behavior. Now, the gas laws that we've seen up to this point, Charles's law, Boyle's law, and Avogadro's law, say, here is a situation. What happens when I change it? The ideal gas equation doesn't do that. What it says is, here is a bunch of data, find the missing value. So we can use this to find the pressure, or the volume, or the number of moles. In fact, if we know the number of moles, then we might even be able to guess things like mass and formula mass, which will lead us to identity, or the temperature. P is the pressure. If we use this in atmospheres, it's going to build into a special value here for R later. So the way that we mostly use this is that pressure is in atmospheres, volume is in liter, N is in moles, T is in Kelvin, which means the value of R, which is the universal gas constant, will be in liter atmospheres per mole per Kelvin. And when that's the case, the value of R is 0.0821. Okay? If you go and you dig and you look in the text, in not our textbook, but in other textbooks or on the internet, you will find different values for R. R is a constant, and it means the same thing, but we use it if we were to read pressure, instead of being in pascals, if we read that in millimeters of mercury or bars or in pascals, we would have to use a different value of R. So if I had a 1 liter canister and was told that that 1 liter canister that contains half a mole of gas will explode if the contents reach 25 atmospheres. So I have a volume, a number of moles, and a pressure. The question is, at what temperature will this gas can explode? I have PV equals nRT. R is a constant, so we can always look that one up. It's not part of the calculation. It won't be mentioned in the question. So PV equals nRT. P is in the question, V is in the question, N is in the question, T is what we have to find. If PV equals nRT, then I have to move N and R across the equal sign, which pushes them from being numerators down to being denominators. So PV over NR is equal to T. And as long as I've got my units correct, those numbers should just work. So pressure is in atmospheres, volume is in liters, moles is in moles, R is in liter atmospheres per mole per Kelvin, which means temperature is going to come out in Kelvin. 25 times 25 atmospheres times 1 liter divided by 0.5 moles times 0.0821 liter atmospheres per mole per Kelvin gives me 609 Kelvin. If I subtract 273 from that, it tells me 336 degrees Celsius. So there is absolutely no danger of that gas canister exploding under normal environmental conditions, because, you know, a hot sunny day is 30 degrees Celsius. So this would only explode in the case of a fire. Dalton's law of partial pressures tells us that because the gas particles are acting independently, that a mixture of gas behaves just the same way that a pure sample of gas does. So the total pressure of a gas mixture is equal to the individual pressures of the gas components. We call the gas components pressure partial pressures. So, question, what is the total pressure of a mixture of gas that is 2.5 atmospheres of nitrogen mixed with 0.25 atmospheres of oxygen? Well, the total pressure of the gas mixture is equal to the partial pressure of nitrogen. This little apostrophe here tells me that's a partial pressure, plus the partial pressure of oxygen, which is 2.50 plus 0.25. Just to add the numbers together, the total pressure inside the container is 2.75 atmospheres.